This is a lecture about gases, and it tends to be the topics in the latter half of chapters over gases, covering Dalton's law of mixtures of gases, some gas stoichiometry problems, a little bit more detail about the kinetic molecular theory, and diffusion and effusion. So gases, most of the time, occur in mixtures rather than as pure substances. And gases always mix in a homogeneous fashion. So a mixture of gases will always be a solution. Air is obviously a very common example of a gas mixture. So because of that, we have some laws to follow when dealing with mixtures of gases and trying to find the individual properties of each. So it turns out that because the gases don't interact with each other, there are not significant intermolecular attractions or repulsions, that we can treat each gas individually that's in a mixture. So that works out, makes things a lot easier for us. So if there's a gas in a mixture and we want to talk about the pressure or properties of one individual gas in the mixture, the pressure we refer to as partial pressure. That's the pressure of a gas that's in a mixture. Interesting enough, the pressure of one gas in a mixture is unaffected by the pressure of any other gas in the mixture. The gases really operate independently of one another, so that's real important to remember. It is important to know what fraction of a mixture a particular gas is, and we'll see later that we deal with mole fractions, kind of like what percent is gas A in this mixture. That'll help us figure out its partial pressure. And in order to get a mole fraction, we typically will want to know the number of moles of each particular gas in a mixture. All right, so we're going to start out with Dalton's law of partial pressure, which is a real commonly used equation. And it very simply says that the total pressure of a gas mixture is equal to the partial pressures of all of the individual gases that make up that mixture. Very simple. Well, how do you find out the pressure of any of the individual gases in the mixture? You can still use the ideal gas law, okay? So in the form you're most used to is probably PV equals nRT. We covered that in the first lecture over gases. And just rearranging that a little bit so that we can solve or isolate pressure, you can find the pressure or partial pressure of any gas using the ideal gas law. All right, so let's hope I don't have to stop this because of my dog. So if we take Dalton's law, which said the total pressure of any mixture of gas is equal to the sum of all of the partial pressures of the gases in the mixture, what I've done here is I've simply subbed in the ideal gas law for all the partial pressures. Okay? And the reason I did that, if you follow me through, and you won't have to do this derivation, you can see that in order to get the total pressure of any mixture of gases, really all I need is the total number of moles of the gases in the mixture, because R, T, and V for the mixture is going to be the same. It's going to be a constant. It's not going to vary from gas to gas in the same mixture. So I really just wanted you to see that the total pressure and total moles present are directly proportional to each other. All right, so mole fraction is something when you're dealing with mixtures of gases you have to get comfortable doing. The mole fraction is defined, we use this Greek symbol chi, that means mole fraction, and that's simply the number of moles of the gas you're interested in divided by the total moles of gas. Okay, that's literally mole fraction. And since the volume and temperatures I just went over in the last slide are the same for each gas in the same mixture, you don't have to be able to do this derivation, but if you want to see where this equation comes from, the bottom line, what I want you to know is that the partial pressure of any gas, we'll just call it gas A, okay, equals the mole fraction of that gas, gas A, times the total pressure for the mixture. Okay, so again, look at this for a minute, write it down. This is an important equation to know. the partial pressure of any gas in a mixture, we'll call it gas A, equals the mole fraction of that gas in the mixture times the total pressure. All right, so let's do an example. The partial pressure of nitrogen and air is 592 torr. You may or may not remember from the previous lecture on gases, torr is the same thing as millimeters of mercury, the different units of pressure, and that there are 760 torr, or 760 millimeters of mercury in 1 atmosphere. So just to kind of get you familiar with the units. If the atmospheric air pressure at the time of this reading is 752 torr, now what is standard pressure typically at sea level? It's typically 760 torr, but obviously it varies day to day. You can even call your local weather, and they'll tell you what the atmospheric pressure is. It'll usually be close to 760 torr, but not always spot on. So it's saying what is the mole fraction of nitrogen? Okay, so what is the equation we just learned that relates pressure to mole fraction? That equation said that the partial pressure of any gas, and in this case we're talking about nitrogen, equals the mole fraction of that gas times the total pressure of the mixture. Now the total pressure of a mixture of air is simply atmospheric pressure. Okay? So if you rearrange this equation, you can solve for mole fraction, which is what this problem is asking for. So the equation, which I wrote a little bit too big here, if you rearrange that to solve for mole fraction of nitrogen, it would tell you the mole fraction of nitrogen is simply partial pressure of nitrogen divided by the total pressure of the gas mixture. So I'll go ahead and solve that on the next page. All right, so we can get the mole fraction of nitrogen gas, okay? And that's defined simply as partial pressure of nitrogen divided by the total pressure of the gas mixture, and that was given to us. So the mole fraction of nitrogen is 0.747. Here's a much more challenging example. Working with Dalton's law and mixtures of gases. It also requires the use of Boyle's law. I'll give you a little hint here. If you feel up to a challenge, you might go ahead and try it yourself. It's real rewarding to be able to figure it out your own. But I will walk you through it also. So you have a situation, which is not uncommon if you're doing a reaction between different types of gases, where you have, in this case, 3 different gases, and they're isolated. These are considered, these little X's represent valves that close or isolate the gases from one another. And the pressure, the complete pressure, because they're isolated, they're not a mixture yet, of each of the gases in the chambers. And if the valves are opened, the gases are all going to diffuse and mix with one another. And the question says, what is the partial pressure of each gas and the total pressure once the valves are open? So, as a hint, you need to ask yourself, what's changing when you open the valves? Well, clearly pressure is going to change, but what has changed to cause pressure to change? There's going to be a big change in volume. Okay? So right away we've got a change in volume, and as a result of that, a change in pressure. Whose law have we learned, or what law have we learned that involves changes in volume and pressure? That would be Boyle's law. Okay, so hopefully you've written these down. So Boyle's law told us that P1V1, pressure under one set of circumstances times volume under the same set of circumstances equals P2V2. It told us that pressure and volume are indirectly related to each other, inversely related. If volume goes up, as in this case when we open the valves, the pressure will go down. And so you should expect to see the pressure of all of these gases go down when you're increasing the volume. So if you have an idea to do it, I would challenge you to try it on your own. I will walk through it with you on the next page. All right, so the first thing that you want to do is use Boyle's law to calculate the new pressure of each of the gases because the volume has changed. So using the P1V1 equals P2V2 and starting with methane, CH4, the original pressure of methane in the small container was 2.7 atmospheres and it was a 4-liter container. We're solving for, as the problem asks us to, the new pressure of methane once the valves are open. Once the valves are open, it's no longer a 4-liter container. The gas has access to all 3 of those open containers, and so we have to add together the total volume. When we solve for the new pressure of methane, CH4, when it has access to this much increased volume, we get that its new pressure is 1.2 atmospheres. Notice that the new pressure went down, it decreased. You would expect pressure to go down because volume increased, went up quite a bit. We can do the same exercise for the other 2 gases, nitrogen and oxygen. Both of their pressures also go down. This problem asked us the new total pressure, and so the new total pressure would just be adding all of the partial pressures together. Okay. All right, and so that would give us a new total pressure of 2.26 atmospheres. So not hard if you know what you're doing, but it kind of gives you an idea. The type of problems asked in this chapter often mix multiple gas laws. Right, vapor pressure is a concept I found can be really tricky to get a handle on. Questions over vapor pressure are typical conceptual rather than any type of calculation. So let me do my best to give a real simple explanation of this and see if you can get a handle on it. The vapor pressure, well, first of all, any liquid has a vapor pressure. So look down at the picture at the bottom for a minute. Let's say we have a container of a liquid, water, any liquid. At any point in time, that liquid is going to have some gas molecules over the surface of it. So if you have a glass of water in your hand, there are going to be some gas molecules hovering over the surface of that liquid water. And those gas molecules, as any gas molecules, exert some type of pressure. All gas molecules do. And the more gas molecules there are, the more pressure they're going to exert. Well, that pressure that those gas molecules exert is called vapor pressure. So vapor pressure, the bottom line is the pressure that gas molecules exert that are hovering over a liquid. And the reason we care, the reason we measure vapor pressure, it gives us an idea of how easy or hard it is for that liquid to evaporate. Okay? If you spill a glass of water on a surface and you come back sometime later, you're likely not to see the spill. It would have all evaporated. If you spill something like gasoline, it's going to evaporate pretty quickly because there's a pretty high vapor pressure. There's a pretty high tendency for gas molecules to escape from the liquid phase to the gas phase. If you spill oil, it's going to probably stay there for a long, long time because the molecules of an oil liquid have a very low vapor pressure. They don't tend to want to escape into the gas phase. So it gives scientists a good feel for changing phases for a liquid. Obviously, as you would expect, vapor pressure increases with temperature. That's usually a multiple choice on your test. You would expect that, right? If you spill hot water, you would expect it to probably evaporate faster than if you spill ice water, okay? The individual molecules have more kinetic energy and are likely to be able to escape quicker. Just like you, if you need to run and you haven't slept all night, you have low kinetic energy, you're less likely to be able to escape if somebody's chasing you. All right. Why are we even learning about vapor pressure? Well, it has to do with gases, but the most common place you will use it in this chapter is, let's say you're doing a chemical reaction, and let's say I'm doing a chemical reaction in this Erlenmeyer flask, And this chemical reaction generates a gas, and I want to trap this gas. As you can imagine, if you just leave the container open in the atmosphere like we do most chemical reactions, it's just going to escape into the atmosphere. So if one of your products is a gas and you want it, you've got to close your system and typically have a tube that the gas can travel through, and you need some way to trap that gas. Well, a common way to do that would be to lead a tube into a vat of water. You can monitor the gas formation because you'll see bubbles forming in the water. And then if you invert a container in that vat of water, and you originally fill that container with water, so let's say it's all full in the beginning, you can actually monitor the volume of gas you're collecting, because what will happen as the gas bubbles into this inverted container, it'll displace the water. The water will start leaving the container, going back down into the open vat, and the container will fill up with gas. And so you have a way to collect your gas to measure the volume of how much you've made, but it will be wet. It'll be contaminated with water vapor. And so in order to, before you can calculate exactly how much gas you have to account for the wet water vapor mixed in with it. So we use Dalton's law to do that, okay? So just to kind of repeat what I said in the last page, when you collect a gas over water, the gas you're going to collect will be mixed in with water vapor. You need to account for that. You're going to use Dalton's law of partial pressures, which basically says you're going to have the total pressure of the mixture of the gas you're collecting in water. And if you subtract from that total pressure the pressure due to the water vapor, you will then be able to calculate the pressure of the gas that you're collecting, which is what you want. Okay? So that's Dalton law. It's just basically saying when you add together all the partial pressures of your mixture, you get the total pressure. How do you find out the vapor pressure of water? Okay, there is a tape that's been monitored like crazy. The only thing the vapor pressure of water depends on is the temperature, and so there are tables of data handy for you where whatever temperature the reaction took place at, you can look up and find out what the vapor pressure of water is. I'll show you on the next page. Okay, so for example, let's say you're working at room temperature, which is around 25 degrees Celsius. That's a good number to know, to remember too. Usually that'll be in Kelvin when you're working in gas laws, so 25 degrees Celsius, same thing as 298 Kelvin. And the partial pressure of water at 25 degrees Celsius is 23.78 milligrams of mercury. Okay, and so that would be the partial pressure for the water vapor that you collected at that temperature. So let's do an example. Let's say that we have, and remember that you need to be able to name compounds for this next test. So I'm hoping also that you have been keeping track of polyatomics and their names. There is a memorization folder now posted in D2L where you can see everything you need to have memorized for the next test. But this would be called ammonium nitrate. It's an ionic compound. And we're going to heat it. This little triangle for chemists means heat. And it's going to decompose to give us, I'm hoping you can name this, dinitrogen monoxide and water. Dinitrogen monoxide is a gas, you can see from the G symbol, and we would like to collect it. And so the question says, what volume of dinitrogen monoxide collected over water? Of course, they're going to give you the temperature. That's so that you can figure out the pressure due to the water that's going to be contaminating that gas. They also give you the total pressure. You're going to use Dalton's law, obviously. And they give you the starting amount of the ammonium nitrate. So this is probably tricky. You probably need to watch me work it before you can do one on your own. Just a couple of comments to get you to kind of analyze what's being asked. It's asking for the volume of the product, dinitrogen monoxide. Okay, so it's really a stoichiometry problem. Anytime you're asked for amounts of product, it's some type of stoichiometry. So I don't want you to get so overwhelmed with the pressures and other information. And so what I would do as always is you weed through all this information, and I would start with the given, which is the amount of the reactant you started with. I would start with that and convert this to moles, and then hopefully to volume of N2O before I did anything else. All right, so the given amount of ammonium nitrate that you started with, 2.6 grams, divide by the molar mass of ammonium nitrate in order to get the moles of ammonium nitrate started with. Then look at the mole ratio of ammonium nitrate to the product you're interested in, dinitrogen monoxide. They are present if you look at the balanced reaction in a 1-to-1 mole ratio, and that tells you that this reaction can make the theoretical yield, in other words, is 0.032 moles of dinitrogen monoxide. Okay. They want to know the volume, however. Since it's a gas, often chemists want to know the volume of the product instead of moles or grams, because that's the easiest way to measure how much gas you have is volume. And so there's more to this, but if this were a free response question, you would probably get half credit just making it this far. Alrighty, so now gets a little bit of a tricky part. At this point, you have to realize anytime you collect a gas over water, which is pretty much all the time, you will have a situation where you have a mixture of gases. You have the gas you want, the product dinitrogen monoxide, but it'll be contaminated with water vapor. So you have to use Dalton's law to figure out what the contribution from the gas you want is. And so just rearranging Dalton's law to solve for the dinitrogen monoxide pressure, which is what you're interested in, is what we've done here. The problem gave you the total pressure as 94 kilopascals. I'm going to convert that to atmospheres so that all of our units match. And so this whole portion is simply the total pressure. We're going to subtract from the total pressure the pressure due to the water vapor, which either the problem will give you or you'll be given a table of vapor pressures. The problem did tell you the temperature, so if you look at the temperature, the pressure for water vapor at that temperature is 21 torr. Again, converting it to atmospheres so that all the pressure readings are in the same units. So now if you take the total vapor pressure or the total gas pressure and you subtract from that the water vapor pressure, you will in fact get what you want, which is the partial pressure of the dinitrogen monoxide, which is 0.90 atmosphere. That's awesome. Now you've made your way to the pressure of dinitrogen monoxide. However, the problem asks you for the volume. Anytime you have one property of a gas, let's say pressure, and you want to get to another property, let's say volume, you use the ideal gas law. Okay, so that's what this is. It's an ideal gas law. You plug in all your volume or all your data, making sure that your units match. So there's the moles you calculated from the last page using stoichiometry. Here is your universal gas constant value, R. Make sure your temperature is in Kelvin and the pressure you just calculated. So if you plug all those numbers in, you see then that the volume of the dinitrogen monoxide product is 0.87 liters. So that's your final answer.